All right, so let's talk about the momentum equations for the wind-driven gyres. If you remember from your physics class, force is equal to mass times acceleration. We're going to use those relationship, Newton's second law, but now we're going to write it in a slightly different way. Instead of writing F equals ma, we're going to interchange the order. We're going to say ma is equal to F. But more than that, we're going to write that equation per unit volume. So what used to be the mass will become the density rho. So we'll have, everything will be per unit volume. So we'll have rho times the acceleration is equal to the forces per unit volume. All right, so that's what we're going to do. And we're going to write the x component of momentum and the y component of the momentum, x being eastward, y being northward, and we're going to do everything in Cartesian coordinates, neglecting the effect of sphericity, which are small to first order. And that way we can focus on the essential physics without having to worry without all those spherical coordinate sines and cosines. All right, so what's the momentum equation? So the x momentum equation is what I said, mass times acceleration per unit volume, so rho naught times the acceleration, which is du dt, plus v vector grad u minus f times v. All right, so what's all these u's and v's? I guess the velocity v is u, v, and w. So u is the x component of velocity, v the y component, and w the z component. Z points upwards, v points northwards, and u eastward. So the momentum is just rho times v, momentum per unit volume. Per unit volume. So I'm not always going to mention that things are per unit volume, but you can always figure out what we're doing by looking at the units. All right, so density times the acceleration is equal to the forces. So we have the pressure force minus dp dx. And then we have minus the divergence of the stresses, the small scale turbulent stresses. And these, we're going to write them in vector form as, well, maybe I'll just write as a vector, tau x. So why is it a vector if it's the x component? Well, it's because you can have eastward transport of the eastward component of momentum. You can also have the northward transport of the eastward component of momentum, and you can also have the upward transport of the eastward component of momentum. So this stress is really a tensor, and here we're only taking one part of that tensor, which is all the stresses, the stress tensor, all the components that have to do with eastward momentum. And so these, the way we parameterize this one, tau x, we will write as a vector tau xx, tau yx, and tau zx. And we can think of this as eastward flux of eastward momentum, northward flux of eastward momentum, upward flux of eastward momentum. And the way we parameterize these, we will assume that they are molecular diffusivity. So it'll be a down gradient flux, a Fickian flux. So if you have a region with a lot of momentum here and less momentum here, then the idea is that the turbulence will try to smooth out the momentum or eliminate the gradients and transport the momentum from a place where there's lots to a place where there's less. All right, so that means we will parameterize these things in terms of the shear, the gradient of the velocity. So we will write it like this, rho naught times AH du dx. Right, if there's a gradient in the x direction of eastward momentum, then there will be a flux down the gradient, so we'll put a minus because it's down gradient. AH du dy and AV du dz. Now, why do we have two components, AH and AV? Is because it turns out that the diffusivity for momentum is a lot larger in the horizontal direction than in the vertical direction. So there's two reasons for that. One reason is that eddies that overturn in the vertical, they have to lift up dense water from below and bring it up, and at the same time push down more buoyant water down into below. And so to do that, you have to do work against gravity, and that means that the overturning eddies will lose some of their kinetic energy into potential energy by lifting heavy water and upwards and pushing light water downward. That's because the ocean is stratified with more buoyant water at the surface and denser water, less buoyant water deeper down. So that's one reason why the overturning eddies are generally less energetic, and therefore you get a smaller diffusivity. Another reason is that it has to do with the scales of motion. The horizontal scales are so much bigger than the vertical scales in the ocean. So the typical depth of the ocean is about 4 kilometers, so 4,000 meters, but the horizontal length scale is maybe 4,000 kilometers, which is 4 million meters. So there's a factor of at least 3 in the horizontal scales compared to the vertical scales. And that means that eddies are a lot freer to move horizontally than in the vertical direction. Of course, these eddy stresses are also parameterizing not just the turbulent mixing, but also the effect of waves that will radiate away. So if you have lots of momentum in one place, that momentum can radiate away through pressure forces and will transport it to other parts of the ocean. So that's another way in which the small scale motions will lead to a diffusive flux of momentum, or that's just a way of thinking about it as diffusion. So these numbers AH, these are called diffusivities for momentum, and the typical sizes for AH.
All right, so AH ranges from 10 to the minus 1 meter squared per second, all the way up to 10 to the 3 meters squared per second. So that's the kinematic viscosity
meters squared per second.
in the horizontal direction.
One is much smaller.
And then AV ranges from 10 to the minus 4 meters squared per second, all the way up to 10 to the minus 3 meters squared per second.
Meter squared per second. So there's maybe a factor of 10 to the 6 difference at the high end, and maybe 10 to the 4 at the low end of these diffusivities. So horizontal are much more important, but at the same time, these vertical scales are much smaller, and so you don't have to mix things as far in the vertical. All right, so what we can do is we can substitute this expression for this stress over here into the divergence term and get an expression in the x momentum that involves only the u and the v velocity components, I guess, in v. So let's substitute that in there. So the divergence, that's like d by dx of the first component plus d by dy of the second component plus d by dz of the second component. So rho naught and h are constants, you can pull them out. So what I'll get is the second derivative with respect to x, the second derivative with respect to y, plus the second derivative with respect to z. So if I substitute that in here, what I end up with, the minus and the minus becomes a plus. I have the rho naught, the ah, and I have the second derivative of u with respect to x squared plus second derivative of u with respect to y. And then plus rho naught av, the second derivative of u with respect to z. All right, so that's my x momentum equation. I'm now going to write the same equation, but for the y component of momentum. So that is going to be y hat rho naught. Now I'm using v plus v dot grad v plus fu. Right? Notice how the signs flip here. For the Coriolis force is equal to minus dp dy plus, and here I'm going to write again minus the divergence of the stress, but now the y component. So how am I going to parameterize that one? So that's tau y, and that's going to be minus rho naught ah dv dx ah dv dy and av dv dz. So same idea as before, except what used to be u for the x component of the stress now is y for the y component of the stress. And again, if I take the, this is the divergence. If I take the divergence of this, I'll get d by dx of the first term plus d by dy of the second term plus d by dz of the second term. Substituting in, what I end up with is, again, minus minus makes it a plus, rho naught AH d2v dx squared plus d2v dy squared plus rho naught AV d2v dz squared. All right, so now we want to look at the scalings of different sizes of different terms. So let's look at this nonlinear term. This one is a mean, nasty nonlinear term, which is hard to deal with. Fortunately, it turns out to be small compared to the Coriolis force, so I want to show you that that's indeed the case. So what we're going to do is called a scaling analysis. A scaling analysis. And what we do is we put in the typical sizes for v and the v component, v vector, and v component, u component, f and u, and we compare the ratio of these two terms. So if I take the advective term, v dot grad v, over this term, f u, and I plug in the scales in here, well, the velocity, the typical scale is going to be like u, and v is also scales as u. The gradient is like a derivative in space, so that'll go like 1 over the length, L, divided by f times u, or u over f times L. Now that quantity, we can now put in some scales. What do we know? Well, in the gyres, I told you that away from the boundary currents, the typical velocity scale is about 0.1 meters per second, so that's 10 to the minus 1. F, the Coriolis parameter, is about, oh, this is in meters per second. This one here, 10 to the minus 1 meters per second. F is about 10 to the minus 4, 1 over second. L is about 3 times 10 to the 6 meters. So if you look here, you have meters per second on top and meters per second on the bottom. So all the units cancel out. So this is a dimensionless number. So it's a pure number, there's no units, no dimensions. And we define it as the Rossby number, rho, and that's the Rossby number. And if this number is small, then that means that the advective terms are small compared to the Coriolis force. If that number is big, that means that, or of order 1, that means that the advective terms are important and can't be neglected. Okay, so what is the scale of this? Well, 10 to the minus 4 times 10 to the minus 6, that becomes 10 to the minus 2. Sorry, 10 to the plus 2. I bring it on top, it becomes 10 to the minus 2. That gives me 10 to the minus 3, or 1/3 times 10 to the minus 3, or 3 times 10 to the minus 4, roughly. So that's very small. So indeed, these nonlinear terms are small compared to the viscosity. So we're on the large scale in the gyre, the Rossby number is small, and so we can neglect these nonlinear advection terms. So that's a nice thing. So we can just worry about the rest of the terms. And the first term, which has to do with the time derivative, we're going to also assume that these are small. So we're thinking of long time scales, like climatological time scales, many years, where the gyre, we're just kind of get the mean dynamical balance that leads to these gyres that are pretty permanent. So they change a little bit in time, but they're always there. You take a ship out on the Gulf Stream and there's always a Gulf Stream. It doesn't disappear from one year to the next. So these terms here, we're going to neglect these terms, assuming we're in a steady state balance. These terms we're going to neglect because they're small in favor of this one. And now the first balance we want to talk about is one called the geostrophic balance. And that one says that the pressure force, whatever it is balanced by the Coriolis force due to the geostrophic velocities. So if we do that, we have the following balance. So the geostrophic balance is the balance of this with this and this with that, where the Coriolis force is due to the geostrophic velocities. So we're going to write rho naught F times V geostrophic with a minus is equal to minus dP dx. So that kind of defines the geostrophic velocity. It says that whatever the pressure gradient is, there's going to be a geostrophic current that balances that pressure gradient. And the other term in the other equation will be plus rho naught Fu geostrophic is equal to minus dp dy. So it's interesting that we use the x momentum equation to learn about the northward component of the geostrophic velocity. So the eastward momentum equation tells us about the northward geostrophic velocity. Similarly here, it's the northward momentum equation that tells us about the eastward geostrophic velocity, right? And that's because the Coriolis force acts perpendicular to the direction of motion. All right, so that's the geostrophic velocity. If these pressure forces are balancing the geostrophic velocities, there may be other velocities that are not in geostrophic balance. And in fact, there are, and an important one is the Ekman velocities. So the Ekman balance, and that one is where this vertical diffusive flux divergence of momentum balances the Coriolis force due to the Ekman velocities, and where this same thing, this vertical diffusive flux of momentum of the Ekman velocities is going to balance this Coriolis force. So what we have is minus rho naught F v Ekman is equal to rho naught AV d2 U Ekman dz squared, and plus rho naught Fu Ekman is rho naught AV d2 U V Ekman dz squared. All right, so the full velocity U, I guess, is good. Oh, I can't see up there. U is equal to U geostrophic plus U Ekman, and V is V geostrophic plus V Ekman. So if I substitute in here, then I balanced off this term, and this term, this term, this term, and this term. I've neglected these horizontal diffusive terms. So the idea is that we're on scales where large but not too large, so that these horizontal gradients here are negligible. So these d by dx squared and d by dy are small compared to these vertical ones. Okay, we'll bring back these terms later when we think about the gyre, when we get to the western boundary current. These terms will become important again. But for now, we can neglect those. All right, so we have these two types of balance, the Ekman balance and the geostrophic balance. And in the next video, we're going to look at the Ekman balance. We're going to study that a bit more. All right, so that's all I have for now.